coming back. So we're continuing this lecture with this example. So remember, we were looking at this particular degree 8 K3 surface. And then if you take the involution, which flips the signs of either the first or last three of the variables, then the quotient is an Enrique surface. And what we saw last time was that the Étal-Brouwer set was empty, and hence there were no Q points. And the algebraic Brouwer set was non-empty. But when we defined these sets in general, in between, there was the full full Brouwer set, using the Brouwer-Monod obstruction from the full group. So the natural question that's left open is, what about this set? Okay, so I gave the answer away last time. So what happens in this example is that actually the Brouwer group is purely algebraic. So over Q, there are no transcendental Brouwer elements. And so just that means that these sets are definitely equal. This Brouwer set is non-empty. Okay, and this equality, I mean, I called it a theorem, so hopefully you're giving me the benefit of the doubt. This is not for stupid reasons. It's not because the Brouwer group over the algebraic closure is trivial. There are actually elements there, and what we show is that they are not defined over Q. Okay, so what we've seen in many of the lectures is there's this general theme that transcendental elements are very hard to understand. So I can't dive right into how we study this particular surface. What I want to first talk about is what are the tools we have at our disposal in general. So general tools for, let me say, Brouwer X bar. And in this, X will be a smooth variety. And the ground field will be algebraically closed. Oh, I guess this doesn't matter. I'm just going to put bars everywhere. Characteristic A equals 0. Okay, so one of the first tools, we saw a lot in Verily Alvarado's talk. We get that from the exponential exact sequence. So the Brouwer X bar fits in the middle of an exact sequence with H3XZ torsion. And on this side, we get Q mod Z to the second Betti number minus the Picard rank, and the geometric Picard rank of X bar. Okay, so this is something general that, assuming we know enough about the geometry of X bar, which we do in these situations, we immediately know the structure of Brouwer X bar as a group. Okay, it's not nothing. Okay, then what about when we look over the ground field? Well, just by definition of the algebraic Brouwer group, if we look at Brouwer X mod Brouwer 1, we get an inclusion into Brouwer X bar. And not only do we know it lands there, but it lands inside the Galois invariant part. Okay, so if we know the structure of Brouwer X bar as a Galois module, then that also shrinks this down even more. And I should say, this actually does a lot of the work. So a result of Kotelin and Skorobogatov says that the co-kernel is finite. Okay, so this deals with all but finitely many of the elements for you, assuming you know the structure of Brouwer X bar as a Galois module. Okay, so let me speak a bit philosophically for a minute. So we want to try to understand these transcendental Brouwer elements, but the way we should think of Brouwer classes in general is that they really don't want to exist. They don't want to hang around. They're not friendly. They don't want to talk to you. We should think of them as only being there if we forced something to happen. Okay, so Brouwer X bar, by the geometry, Brouwer classes are forced over the algebraic closure, but over any given number field, they should not want to be there. Okay, and as a partial justification for this, I'm going to piggyback on what Verily Alvarado was talking about in his talk. So if you have a degree 2 K3, then we should think of if you fix a point in here, that's giving you a degree 2 K3 surface. So then the Brouwer classes will correspond to fibers above this. So if I take a Q point here, the fiber will be a zero-dimensional subscheme of degree 2 to the 9th times 2 to the 10th plus 1. And probably, if your point is general, that will be basically completely irreducible. So you don't really expect those things to be defined. But also, even if they are defined, even if you do get lucky enough that there is a rational point above here, remember this is morally what happens. We don't actually know these moduli spaces exist, but bear with me. So assuming they exist, I think probably many of you in the audience have studied that there is a difference between field of moduli and field of definition. Just because the point in the moduli space is defined over Q does not mean you get an actual object over Q. It just means you get a Galois invariant thing. So a rational point over one of these fibers will tell you that there's something here, but then Brouwer classes really don't like you. They still really do not want to be in the image of this map. Okay, so, and this is all philosophically. So this result, in some sense, this should be what we hoped to happen because we didn't rig anything particularly to control the transcendental elements. Of course, we don't know that something else we rigged didn't force this, but hopefully we didn't do anything to make them want to come hang out with us. This is probably what will happen. So, but we need tools to be able to prove this. I can't write in the paper, well, Brouwer classes are really unfriendly. They don't want to be there. That doesn't work as a proof. So we want tools to be able to write down the Brouwer classes, but also to be able to determine whether or not they descend. Okay, so I'm going to continue. If X is a K3 surface, then the left-hand side is finite. This is in general. I think it's completely in general. Maybe I need a surface. Okay. So if you were keeping track of the dates, one thing that might have seemed kind of surprising is that all of the results people have mentioned about Brouwer groups have come maybe the earliest in the mid-2000s. But there was this result of Skor-Bogatov in 1999 where he produced a bielliptic surface with empty étale Brouwer set and non-empty Brouwer set. So how did he do that? Well, the bielliptic surface, you have a lot of structure coming from the product of elliptic curves that dominates your surface. And so using that, he was able to write down elements which generate Brouwer X bar. But then in his example, the Galois invariant part was completely zero. So this question of asking whether something descends or not, just because it's fixed by Galois, does that mean it's defined over K? That was not needed. I mean, it was still, it's still hard to write down the elements. So we have two hard problems: write down the elements and then also determine if the Galois action is enough. So now let's specialize. So these are general tools we have. Now let's specialize to the case when X is an Enrique surface. So what do we know about the geometry of Enrique surfaces? Well, I didn't state this, but you can prove or find in any reference on algebraic surfaces that for an Enrique surface, the Betti number is equal to the Picard rank. So this part, this big infinite part, goes away. That's pretty good news. And H3xz, well, it better not be 0, because I told you, I promised you that this was not because of silly reasons. It is indeed non-zero. It's C mod 2. Okay, so you first see this and you're like, oh my God, that's so awesome. It's as small as it could possibly be. How hard could this be? It's one element. How hard could this be? So we immediately see the first problem, that the Galois action does absolutely nothing. Absolutely nothing. This half of our general tools can no longer be used. Okay, so one idea is, okay, so part of the problem is we went so far up. We went all the way to the algebraic closure that so many of the other classes were killed. So to deal with the C mod 2 problem, an idea is to find a number field, say K over Q, such that there, the algebraic Brouwer classes are not just the constant classes. So you have some interesting classes, and that now when I look at the quotient over K, so I have some extra classes, this is no longer going to be just a Z mod 2. Then when I take the Galois invariant set here, this is contained in just the algebraic Brouwer group. Okay, so this is one way that I can overcome this C mod 2 problem. But now I have to work over a number field. I can't use any analytic techniques at my disposal. Okay, so this seems like a pretty good strategy. So now we're led to the question, well, first of all, maybe we can compute this as a group, but we also want to understand its structure as a Galois module. And then, so the way I want to understand its structure as a Galois module is to actually represent the classes as central simple algebras. So that leads us to the question, how do we write down Brouwer classes? Question? Oh, yes, thank you. Brouwer K. I don't know if that helps. I probably should have just crossed it out. How do we write down Brouwer classes? But then also, not only how do we write them down, but given a Brouwer class, how do we determine whether or not it's fixed by Galois? So given an alpha in the Brouwer group, I'm going to be a little vague here. How do we determine if alpha minus sigma of alpha is trivial? So trivial, your favorite definition of trivial. Maybe how do we tell if it's equal to 0? How do we tell if it's a constant class? You could even ask, how do we tell if it's an algebraic Brouwer class? How do we do this? Determine, not determinant. Okay, so, well, this question, I hope what this question is reminding you of is that we have in the Brouwer group a sum of central simple algebras, and we're asking how we reduce it, how we figure out a minimal type of representation for it, which makes it easy to determine whether or not this is in this subgroup. And then hopefully you also remember that I told you in the first lecture that that is a very, very hard question. Forget about surfaces or anything, just if I give you something like this, how do you represent it in some minimal fashion, which makes it easy for you to determine whether or not it's in a subgroup. So now let's recap a few instances where we have tools to determine whether or not an element is trivial. So let's recall from the Brouwer group of fields. So what are some tools we have to determine when the Brouwer group is trivial or to figure out how to write something in a nice fashion? Well, one of them was looking at cyclic algebras. So we saw that if L over K, little k, is a cyclic extension, then the kernel from the Brouwer group of K to the Brouwer group of L, what's also known as the relative Brouwer group, this is isomorphic to K star mod the norms. And the map takes in class B and sends it to the cyclic algebra sigma B, where sigma is a fixed generator of L over K. Okay, so this is still not completely trivial, because to determine whether something is trivial, we have to figure out whether it's a norm, but at least it's some general machinery. Maybe for special types of extensions, we have some tools that we can use. So what's another great tool that we have? Well, we have the purity theorem, and it's especially useful. I mean, it's useful for lots of varieties, but for this question, it's especially useful for rational varieties. And then we get, so let's let S be our rational variety over characteristic zero field. And that tells us that we can look at the Brouwer group of the function field of S, and for all of the codimension 1 points, we can take the residue at those points. And the only elements with trivial residue is the Brouwer group of the total space, that the total space is rational, and the Brouwer group is a birational invariant. So now we just get, for smooth, I should say smooth projective, we just get Brouwer 0 of S, which is, yeah. Okay. So for cyclic algebras, we can tell if something is trivial by testing whether this B is a norm. And for the function field of smooth projective rational varieties, I can test if something is trivial, where trivial means a constant algebra, by testing whether it has trivial residue everywhere. Okay. So the point that I want to drive home in this talk is that these two tools, the purity theorem and cyclic algebras, on their own, they are both incredibly useful. But together, they are even more useful. So basically, we're going to just squeeze all that we can get out of these tools. We're just going to use them over and over and over and over and over again. And they're going to give us many tools for understanding Brouwer classes. Okay, it is probably, maybe possibly, not obvious how these two tools can have anything to do with our situation here, because these are field extensions. How am I going, I said it's hard to determine whether something is a norm, and also the varieties we're interested in are non-rational varieties. And so let me just give a slight historical detour, because this is not the way that these tools were developed. It would have been really cool if someone was just, let's just use these two powerful tools and stick them together. But the path was a little bit more meandering, as is typically the case in research. So what happened was we realized, we being mathematicians, not me, us, realized, well, we know a lot about descent of elliptic curves. And so if we have a surface which has any kind of structure fibered into elliptic curves or hyperelliptic curves, and we can understand the Jacobian, we can use these number theory classical tools from descent, studying ranks of Jacobians, and we can leverage that for the Brouwer group. Because if you have a genus 1 fibration, the Brouwer group is very closely related to the Tate-Shafrovich group of the generic fiber. And a lot of work has been done on that. So there was work, so in Skorobogatev's book, and Wittenberg used this in an example, and Hieronymu took this point of view when he was studying diagonal quartics. And then I was working with Brendan Kreutz, and we wanted to try to generalize this to remove some of their assumptions on the Jacobian. And then what we saw is that these techniques are really best phrased not in terms of having fibrations, although that's useful, but really in terms of thinking your surface having a double cover to some ruled surface, and the ruling inducing a fibration structure there. And then later, from ideas at an AIM conference and this work that Fairley Alvarado was talking about with Hodge theory, so we've realized that you can phrase these things in terms of residues, and now you can view things from this lens, which I think is a little easier to present. I don't have to build up the descent machinery. Okay, so the point of view that I'm going to present is not completely accurate historically, but it's a talk. I'm just telling a story. Okay, so this is the idea. We're getting as much as we can out of these two tools. So what's the setup? So we're going to let S be a smooth, proper, rational, geometrically ruled surface. So what do I mean by geometrically ruled? It's, I think, unfortunate terminology because I don't mean ruled over the algebraic closure. It means that I have a morphism to a curve where not only the generic fiber is isomorphic to P1, but every fiber is isomorphic to P1. Okay. If someone has a better name for this, please let me know, but this is the only thing I could find in the literature. Maybe, but I mean, a P1 bundle, yeah, I guess, but you could blow up, and then maybe you don't want to call that a P1 bundle. So I really want, yeah. Okay, so we take this smooth, proper, rational, geometrically ruled surface and take a smooth, proper double cover. So this does actually work. Much of what I will say goes through if you take any double cover. If you take a cyclic cover of any order, and the parts that are not known to go through right now, one of my project groups is working on, and I think they will tell you it goes through tomorrow. So, all right, so this is our setup, and how are we going to use this here? Well, because S is rational, the Brouwer group of the function field, I can understand mod constants, I can understand through the residues. So this is just direct copy of what I have there. And then what happens because this is a double cover at the function field level, this is a cyclic extension. So I can understand the kernel of this map. So what is this going to allow me to do? Well, it's going to allow me to understand the image of the pullback map on Brauer groups. So I take the image of all the Brauer classes on the function field of Y that arise from the function field of S, and then I just take the ones that are unramified on Y. So I can understand this through understanding residues on S, and it won't, actually we'll see later, I don't have to study residues at all codimension 1 points. I can very quickly restrict to a finite set, and even shortly after that restrict to just considering them on a single curve. Okay, so I can understand this group, but now I have to think, and also this works over any field. So I also understand the elements of the algebraic closure, and then a very, well, amazing thing happens is that this contains all of the two torsion of the surface. Okay. So, and not necessarily, these classes may not all descend, but if I make some extension, intermediate extension, any given class will be defined over some finite intermediate extension from here. So I can study at some finite level and view whichever class I want in terms of residues on S. Okay, and residues, I mean, they're just cyclic extensions of the curve, and since I'm just taking order 2 classes, those are just quadratic extensions of the function field. So I know exactly what the group structure is on quadratic extensions of the function field. I just multiply the functions mod squares. And so the group operation here is very easy to understand. So we're going to leverage these 2 tools to understand this intersection, and then it contains the elements that we're interested in. Okay. Is this making sense? I did not say why. So unsatisfying answer is that you can count and you get everything. Maybe more satisfying answer is, more satisfying, you can prove it in 2 different ways. One is that the image, by looking at cohomology, the image is exactly the parts fixed by this involution, and you can show the 2 torsion is fixed by the involution. Also, this, the point of view in the paper with Kreutz is that we're really studying the Brauer group of the generic fiber, and then you can use some descent argument to show that you get everything. Yeah, so there are 2 points of view. Okay, and let me just say, so the ideas that I'm going to present are sort of mixed up and contained in 4 different papers. So 2 are with Brendan Kreutz. One is with Ingalls, Obis, Osman, myself, and the other is this paper that the theorem is contained in, Balistrieri, Berg, Manus, Park, and myself. And I'm simplifying a lot of the cases, so the things are kind of jumbled up. So I apologize to my co-authors, many of whom are in the room. I won't be so specific about which piece comes from what paper. Okay. So for simplicity, I'm going to restrict to S is P1 cross P1, and B, which will be the branch locus of pi, I'm going to assume is smooth and geometrically irreducible. So then what are some statements we get? Well, first of all, how do we get to reduce to just finitely many residues? So take alpha in the Brouwer group of the function field and assume that pi upper star of alpha is in the Brouwer group of pi inverse of A2. So it's not unramified everywhere, but it's unramified away from the inverse image of P1 cross infinity and infinity cross P1. Then there exists another Brouwer class, not just in the function field, but in A2 minus the branch locus, so it can be ramified on those two curves and also the branch locus, such that the image is equal to the image of this curve. So if I just care about the image of the map of pi upper star, which is what I care about Brouwer classes on Y, it's enough to restrict to looking at Brouwer classes on this open. Okay? And since the Brouwer group of A2 is trivial, the Brouwer group of A2 minus B, mod the constant algebras, this injects into just the residues on the branch locus. Okay, so now I don't have, you might have been worried because you're like, okay, I get the group relation on the residues, but I really don't want to consider this big infinite direct sum. Well, now you don't have to. Okay. So now we've reduced to just considering what this is, but now we want to know which elements are trivial. We know which elements are trivial on S, but we want to know, okay, now when we do this pullback map, we don't want to lose control about being able to determine when something is trivial. Remember, this is our goal. We want to be able to determine when a Brouwer class is trivial. So we don't want to lose that ability under this pullback. Okay. So let's let alpha be in the Brouwer group of A2 minus B such that pi upper star of alpha is a constant algebra. Then there exists a divisor on Y away from the branch locus such that the residue of this algebra is equal to, okay, let me just finish writing and then I'll go back. So it's some function where G is a function on S such that the divisor of this is equal to the push forward of D minus, okay, well, G might not be principal on S, but its principal, the Picard group of P1 is generated by P1 cross infinity and infinity cross P1. So there's some multiple of those that I can add on to make it principal, infinity cross P1. Okay, so I can completely understand the algebras that become trivial through their residues by looking at the divisors on Y. And so this, I don't think I have a picture. So in Verily Alvarado's talk, you saw this Hodge theory complex analytic exact sequence, which showed that elements of the Picard group can trivialize elements of H2 as Brouwer classes. Okay, I didn't say that very well. So these elements of H2Z map to the Brouwer group, and the ones that become trivial in the Brouwer group are the image of the Picard group. So this is like a ramification algebraic statement of that. The divisors on y are trivializing this Brouwer class that came back from P2. So it's the same type of end statement, but different point of view. Okay, so I'm going to prove this second proposition to give you an idea of how these tools come into play. And hopefully you will see that really all we're doing is unwinding definitions. So for simplicity, I'm just going to work over an algebraically closed field, but it's not so important. Okay, so let's take alpha as an element in the Brouwer group of A2 minus B. But I know it's also in the kernel of pi upper star. So when K is algebraically closed, this is trivial. So what does it mean to be in the kernel of pi upper star? Well, we know exactly what these things look like, right? By our tools. Okay, I'll come back to this. This is a cyclic extension. Everything that's killed by the cyclic extension has this form, this sigma comma b. I'm going to write it as a quaternion algebra because a quaternion algebra has exactly one non-trivial element. So this is Fg, where f, the square root of f generates the extension, and g is some element in the function field. Right? Every class that gets killed by pullback is of this form. Okay, well, I know that I'm allowed to multiply g by anything in the norm from this extension, and the norm of square root of f is minus f. So I can certainly multiply by minus f to any power that I want. So after doing this, I may assume that b is not in the support of this function. Right, so f has odd valuation at b, because b is the branch locus of this extension. So I can raise this by some power to make this an even degree, to have valuation even degree, and then I can multiply by squares to make the valuation 0. So I might as well assume that the valuation of g at b is 0. So then, what is the residue of b at alpha? Well, one nice thing about quaternion algebras is I can just swap the order. So now I can think of this extension. This is an extension that's unramified at b. F has odd valuation at b, so this is ramified, and the residue is the cyclic extension exactly given by this. So this is just g restricted to b. Okay, if I take, remember, we're doing this valuation map to get the residue. So we're just really taking the cyclic extension over the fraction field of this DVR, and then we're saying, okay, if it's unramified, then the way I get the cyclic extension of the special fiber is I just reduce it. So I just take this and reduce it. So what I need to prove is I need to prove that this function g has this special form, that it's the push forward of some divisor. So, okay, well, let me just write what the divisor of g is. Well, it's sum of divisors, and then I don't care about what happens at p1 cross infinity and infinity cross p1, so I'll just separate those out. So what we want is that each of these components are the push forward of something. For some divisor on y, right? That's what we need to have happen. So let's remember, what is the push-forward map on divisors? Well, I just take an irreducible curve, I map it down. Oh, I didn't leave myself enough space. And then, but I don't just take the image, I have to take into account the degree of the map, right? So what I put here is the degree of the extension of function fields, the function field of z, over the function field of the image of z. So what do I need to happen in order for this to be a push forward of something? Well, if ni is even, then everything is okay, because I can take the zi tilde to be ni over 2, the inverse image of zi. The map is 2 to 1, so the inverse image will be 2 to 1. So this thing will be 2, and then it will cancel out. But so what if the extension is odd? Then I need a curve which maps 1 to 1 on its image, right? So I have my curve z inside of here. I have some this is my double cover inside of here. And what I want is that there's a curve. The curve above this splits into 2 components, so that one of the components maps 1 to 1. So then I need that the inverse image of zi splits as the union of 2 curves. Okay? So if it's even, everything is fine, but if the valuation is odd, then I have to have this. Okay, I'm just going to rewrite this in valuation theoretic terms. So what this means is for all, instead of thinking of divisors, I want all codimension 1 points, but not, I didn't care what happened at P1 cross infinity, infinity cross P1, or B. So another way to say this is that I want all codimension 1 points in A2 minus B. Okay, so that's my divisor. And I either want, I want either the valuation of S of G to be 0 mod 2, right? That's my Ni being even, or S splits completely in K of Y over K of S. So hopefully these conditions look very familiar. These are exactly the conditions for an algebra to be unramified at S. A cyclic algebra is unramified, remember, if and only if the valuation of the thing is 0 mod the degree of the extension, or it splits completely. So these 2 conditions hold if and only if the residue at S of alpha is equal to 0. And remember, we want this for all S in A2 minus B. Codimension 1 points. And this happens if and only if alpha is in the Brouwer group of A2 minus B. So what did we want to prove? We started with an alpha in Brouwer of A2 minus B. So this was given by hypothesis. So we get that. So we get this. So we get this. So we get this. So this function g, the divisor of it, is exactly the push forward of some divisor minus m p1 cross infinity minus n infinity cross p1. That's exactly what I wanted to show. It was many steps, but all I was doing at each step was unwinding what happened for cyclic algebras and what the residues were. There was no other ingredient to the proof. Okay. Questions? All right. So I did take up most of my time doing that, but what I really wanted to drive home is this point that these two incredibly powerful tools, which are seemingly very special, can be combined to a lot of situations, and just by tracing through the definitions, you can really understand what's happening to these Brouwer classes. So, okay. If we just do more arguments like this, like unwinding all of these steps, I can put them together to get an exact sequence. So I was going to show where this came from, but I think if I do it, I'll rush and then it won't make any sense. So just believe me that you can, by more arguments like this, we're going to be able to get something like this. So for any extension, capital K over little k, we can get the Picard group of y over that extension mod the pullback of the Picard group of S plus 2 pic yk. So this is the way I can get residues which are in the kernel of the pullback map. And then I'm going to relate this to the Picard group on B. So I take P1 cross infinity and infinity cross P1. I restrict them to B. Those give me classes. I look at the quotient, and I take the 2 torsion. This is encoding the possible residues you can get of algebras on Brouwer group of A2 minus B. So it turns out you can't get any possible extension. You only can get finitely many possibilities, and they're encoded by this. Okay, then I'm running out of room because I wrote too big. This goes to the Brouwer group of this open subset of Y, mod Brouwer 0, open subset, and the 2 torsion. Okay, so this is not necessarily surjective. Okay, well, I don't know whether it's surjective. Basically, every case that I know of that has been looked at in detail, you do get a surjection, but those are pretty nice cases, so I don't know what happens in general. But we can, for any given class that I would like to get in here, say over the algebraic closure, I can extend my field of definition, and after an extension, I will get every class I want in here. So it's eventually surjective. Over the algebraic closure, it is surjective. Okay. Let me just make a remark to tie in to Farrelly Alvarado's lectures. So degree 2 K3 surfaces fit into this picture. This is a double cover branched along a sextic. And in that lecture, we saw that there were 3 different kinds of Brouwer classes. So we saw that in a Hodge theoretic way by looking at the lattices. What are the 3 different types of Brouwer classes we get here? Well, this class, this is basically going to be the 2 torsion of the Jacobian and the theta characteristics. Divisors such that twice the divisor gives you the canonical divisor. So the 3 different kinds correspond to the 2 torsion in the Jacobian, the even theta characteristics, and the odd theta characteristics. And there is a very nice story that very explicitly goes back and forth between them. This one corresponds to the double cover of P2 cross P2. This one corresponds to the degree 8 K3. And this one corresponds to the cubic fourfold containing a plane. Okay, so sort of a completely different techniques, but in the simple case of order 2 classes on degree 2 K3 surfaces, the 2 approaches coincide, and there's a nice connection between the 2 of them. Okay, so I'm not going to have any time really to talk about our particular Enrique surface. So it's unfortunate. But what happens, let me just say in words, so this Y is a double cover of a del Pezzo surface, which we already saw in the first part of the proof. And over some sufficient extension, that does become ruled. So you can carry out all of this for the K3 surface and sort of leveraging the picture on the K3 surface to the picture on the Enrique surface. You end up restricting to a very nice subset of this. It's the two torsion of the Jacobian of a genus 3 geometrically hyperelliptic curve. So we completely know the two torsion through the Weierstrass stress points. We can very explicitly understand the Galois module structure. And then we show that we do this idea that I said. Find a number field where the Galois invariant part is contained in the algebraic Brouwer group. Okay, so that's the end of my series. I want to say thank you for staying. It's really been an honor to be here, and I've really enjoyed it and had a lot of fun. I hope you have also had a lot of fun and liked seeing how much fun you can have with Brouwer classes and rational points.